Start, unmute, start. Hello, I hope everyone can hear me. Yeah, so welcome back. We are back on this thing. So yesterday, I think we had to wind up quite rashly. I mean, we wounded up the code very quickly on how to develop the path planning for it. Today, I was hoping we could take a more detailed look at it, and towards the end, we'll start to discuss some other things. Meanwhile, I would also like to show you another plugin called Robots, but that comes with a certain limitation. There are only limited models of robots, and most of the robots available are with academic institutions, universities, and other private and or public labs. So one thing we can look at is how we can maybe develop our own robot model and embed it into the plugin, so that if we have our own so that we can use that robot for our so that we can use the plugin to program our robots. Yeah, normally if any of the labs have the same model, you can end up using that, but if it's a unique model, then you will have to end up making your own model as well. So let's quickly look at that. I think in the drive I had I'm not sharing my screen yet, right? One second, I'm just gonna share my screen now. Yes. So as you can see in the drive, I've shared these two models. One is an MIT sim and an MIT/sim.xml file, and there's a Sacred Heart 3DM model and an XML file. So you need to, once you install the robots plugin, you will need to add these robots. You will need to add this model into your documents, and there is going to be I don't think I'm sharing. I think I need to share my screen. Hold on. Yeah, you will need to add it into your documents folder, and there's going to be a robots folder. You'll need to add all the models and the XML file, and each XML file will contain the details that will allow you to make your own robot or the environment of the robot. So let's take a look at the robot files that we've created. Yeah, so this is a and one second, I'm just going to open this file as well. So yes, so you have all this information that needs to be provided. Namely, you need to give it a robot name. Couple of things that you will need to give is the robot model number. So these are all things that is going to be essential. Apart from that, here, this is the main change that you're going to make, and I will show it in comparison with the model that of the robot that we have in our lab, so that you can compare what it equal to each other. 1 second, I'm going to hold it please together. Yeah, here you go. So here are the few things that you need to change in your model. So the first thing that you're going to create is your own robots model that you can download from the manufacturer. I'll show you that. And the other thing is that you need to change the robot specification, particularly the range, the axis, and all the different details of that. So here, this robot belongs to the MIT and it is named as such. And here I made the change based on the specification that I wanted. The model number I've changed out here, and here you have the model number which is different. And the main changes that you're going to see is the arms and the reaches and the maximum speed. So these are details that you can get from the robot model, or if you can look at Robot Studio. In the Robot Studio, you will find a lot of these details are already available. Particularly the reach and the degrees is something that you'll find within the Robot Studio. And I will quickly show you where you can find the robot specifications online also, wherein you can choose this 6620. Yes, product specification. Product 680 minus 70. All right. So one thing that we can quickly see is the model. And here I'm going to go to controller. Sorry. Modify mechanical jog unit. Angle in which the robot can move. So this detail is provided in the Robot Studio, or you can find it in the product specification also. But the product specification can be quite cumbersome to look at. So this is a shortcut to get the range details within the Robot Studio, because it is specified out here. The other details, particularly to do with uh, the length, the joint positions, and the maximum speed will be found in the product specification. I am just gonna quickly search it out here. What is it? 680. 220, 680. Yes. So what those numbers indicate is the distance between the joints. It is the DH value, if I'm not mistaken. And you will need to configure these figures from the robot. You need to try to configure these figures from the robot. So if I was to open it, compare it side by side, 320 is the figure that you will see from the center of the base to the vertical center of the first axis. Then 680 is the distance from the bottom of the base to the center of the axis. So it's almost like you are tying it up by x and y coordinates from one position to the other position. So you connect from the center of one link, the link number 1, to the bottom, to the first pivot of the first arm. And similarly, you're going to continue. The number 2 is 975 that you can see out here. This is 975. This is the total length of the arm. This is the total length of the arm. And after that, you're going to find the next value. I'm sorry, 1 second. And then after 95, then you're going to find 200. The 200 is from the center of the end of the first arm to the center of axis of the third and fourth, third axis, third to fourth axis, the center line of the lateral arm, the elbow arm. So that is what you'll find 200 out here. Then you'd find the 887 is the total length of the fourth arm to the fifth, from the start of the fourth arm, the elbow arm, to the wrist. That is the total length that you're going to find. And lastly, you will have you'll have the fifth arm and the sixth arm that is required. And these values are going to be configured out here. Similarly, you will find the max speed and the minimum speed of each arm that you will need to configure out here. Let me search for that. Where you will find. See if I can. Yes, this is the axis speeds, robot type, and all the speeds are provided out here. So you need to input all the speeds out here, and that will help you get the motions in place. The other thing that you need to change are these values. These values you'll find them within your robot controller or even in the robot studio. In my robot studio, you'll find it different, but for that you will need to connect the robot into your robot studio to get the details. By default, they are as if you've not changed the name, then you'll find the standard default name, that DO0, DO1 as digital output 0, digital output 1, all the complete set of arrays and digital input. Similarly, you will have analog output and analog input names. So in the case of my robot, we've changed a couple of analog names, so that's why you can see the changes. Otherwise, you'll this is normally the default values. You can have all the way 1 to 16, all the way 1 to 16 out here, and the corresponding analog name. So once you've set this, you've made these changes, you have created your XML file, you've edited your XML file so that you can import the robot specification into your Grasshopper robots plugin. And the other thing that you will have to check for is the other thing that you will have to check for is the robotic model. So this model, again, you can find it within the ABB specifications, ABB model. So I'm just going to search ABB 6620 152.2.2. You'll probably find the 3D model within ABB. Oh, yes. Okay, here, CAD. Here you go. You will find the CAD models or whatever they required. You can get it in different formats. STL is what works best for us, and this is the model that we can download. Step or STL, something like that. We can have the joint model, and once you have downloaded that model, all that is left for you to all that you've left to do is to assemble that model within the specification that you require. Oops. But second, I'm just going to check the model robots model. Yeah. But make sure that you follow the same format, including the same nomenclature. This nomenclature is going to be reflected in your in your XML file. The in your I'm sorry. Yes. This nomenclature that you're going to assign out here, that the robotic arm, ABB IRB 6640280, the exact name and the numbers are you're going to configure out here. The Revolut number 123456, it will be configured the exact same way out here, and you will have your the name written exactly as how you would want it in your model. So once you've made these changes and once you've imported this thing, make sure you convert it into a mesh and save it. Save it as a .3dm file, and you can copy the 3dm file and the XML file into the robots folder in your documents, and now you have the robot ready to be used in a plugin. So I'm just going to open a new file. And I'm going to go in here, import model, load model. And here I have, these are all the available models. If you if one of these models are available for you, you can go for it. And there you go. This way I'm able to import my robot model into the plugin so that I can use the model that I think over time there is a larger collection of different models. So you can utilize the same model. If at all something needs to be changed, particularly in terms of the digital input or the output, you can do it yourselves. So a little bit of editing of the names and this, and you can create your own existing model of this thing. If you have another, say, Bartlett's IRB 120, you can just create a copy of it, change the requisite, at least the arm information would be exactly the same. If you made any changes to the DO and the DI, that is the only change that you would require, and maybe the name, and create a copy of this thing, and you're good to go with another iteration of the model of this model that is specific for your lab or your institute. So there you go. This is one way you can create your own model. Now this is, once you've done that, this is another plugin that I wanted to explore, and this is again fairly a very easy plugin to use. It offers some sort of versatility when it comes to using it, and you have the same bit of commands that is available to us. So I was thinking maybe this session we can try one of the exercises using the robots plugin instead of the robot components. I think that was that is something that we've explored last. But before we get into it, I think one important area. I think yesterday we looked at 3D printing. If anybody has any questions regarding that, we can discuss that. Otherwise, I'd like to take a look at milling, because I think this would be an interesting and kind of tricky way to go about it.
Show how to install the robot in the documents, because I don't have the robot folder in my documents.
Okay.
You can start from there.
You want to
load robot system. So where is the robot library on the computer? How do you search for it?
The robot library is in in documents, in my documents, and there is a robots folder. If you've installed the robots plugin via the Rhino package manager.
Not there.
Okay, Shashank has a question out here because I think he cannot find the robots library folder. Does anybody else get that error? I think yeah, if you I'm just going to open the robots. Yes. So I think if you've installed using the Rhino 7 package manager and search for robots, then it will load everything and will also create the own library. If there is any other reason why you've not got it, maybe there could be a conflict in your Grasshopper. Check your Grasshopper components. If there is already an existing version of it, you might have to remove all of that and then try a reinstall.
Is it a grooming mechanism?
No, the storage of the robots is going to be in my documents.
Could you show how it looks like? Like the folder?
Yeah. So this is my PC, my documents, robots, and here you go. All of this. All right. So I suspect that is not an issue. One second, I'm just gonna close. Yeah. All right. So let's take a look at the milling component. I think yesterday we quickly looked at how we can do the 3D printing. We might even revisit it with the robots component if the robots plugin if time permits. But before that, let us quickly look at the milling script that we have right now. I think I've created a copy for this, and this is the entire script. And here I've created a small. This entire section is just me creating the geometry. We have the plane. I've created some sort of ripple pattern that just moved around the points out here. And then once I've moved around the points, I've just remapped the point and then I've created this ripple pattern. And finally, this is the image that I'm looking at. This is it's a very small and subtle one. I'm just going to increase the yeah. Let me just increase this. Yeah, okay. Now it's a slightly more prominent shape that we're looking at. Maybe it is prominent, maybe it is just yeah. This is the shape that we're looking at. And we want to mill this sort of surface onto any piece of any block of material, maybe a foam or a plywood or a piece of wood or a piece of stone. So there is two components to it, but I'm going to let you all try to figure out one aspect of it. The first stage is if you want to, if it's it's a big sized material that you're looking at, you might have to remove layers of it. The first stage of roughing, where you cut quickly all the bulk of the material without paying much attention to the finishing, and you chop off the bulk of the material quickly. So that aspect is called roughing. And the second component is after you finish the roughing, you start off with a finer tooltip and you go over the parts. You go over the parts a couple of times to get the final finish of that. So that smoothing is what we'll be looking at currently. So we have one of the things that you need to few things that you need to understand is what is the drill bit that you have. And based on the drill bit, you're going to divide your surface into points and or lines, and make sure that you have some bit of overlap, because that overlap is essential for you to ensure that no material is left over. Otherwise, you're just going to create streaks of remainder material, and that's not something that we want. So make sure that when you're configuring make sure when you're configuring the number of the distance between the points that you have, make sure that it is a factor. It is less than the it is less than the diameter of the tool tip. So if it is 6 mm dia, if I'm just going to annotate out here. Yeah. So if this is total length is L, and you have a bit dia of 6 mm, to make sure that L by 6 is the upper limit, and you will want to have you'll need to have this distance less than sorry oops, I'm just going to you're going to have the that value less than you're going to have that value, say I'm going to call this y is going to be less than L by 6, so that the number of iterations you have more than you can create sufficient overlap, and all the remainder material is cut. So, and once that is set, you can move into the dividing it by the geometry. So you can have a look at this code where this could be anything. It could be two curves, and you've lofted and you've created some sort of geometry. And I've just divided that surface into number of points. Okay. Now I'm just going to describe the logic of how we went about this. So you have this surface, and you have all these points at these junctions that is saying. Now the tool is coming from this portion, and it is going to go out here, and then it's going to go out. So you need to create an exit point. So if you were to not create an out point, then what is going to happen is that this after it reaches the final point over here, it is going to go back in the fastest way to the second point, and this we don't need to create. So what is the ideal path that we need to, after its first pass along the first line, it needs to clear the model. So you will create an out point, maybe in the Z direction if it is perpendicular, so that the tool moves from here. This is the tool. It comes here, it goes all this way, and it exits. So that is why we are creating this exit point. And the other thing is, in the continuous set of points that you divided, and if you were to create a line, you will notice that the points start from here, it goes all the way. And this is how lists are in Grasshopper. You'll have all these points. So, and it is named 0, 1, 2, 3, 4. Then what happens in the new list? The next set of lists again starts from here 0. So this is the complete row of 0. This is the complete row of 1s. So once the robot moves through all this set of points, it will again try to restart the list. So even after it's exiting, it will go to the second row, which is down the line out here, and then it will continue across all these points, then clear this points and start from the row again from the beginning. This is a slightly inefficient way of milling. What would be nicer is if you were to go along one path, exit from it. So it would be nice if you had the robot go from this path, go along this line, exit from it, and then go a little way to the left, go in the reverse direction, mill across this portion, and then again exit from it, and then try to create it. So every alternate set of points, every alternate set of point list must be reversed so that you can optimize the travel time and you can optimize the milling time effectively. And this would be quite important if you are to mill a large surface with a large number of points. Every little bit of milling time um, helps helps in reducing the amount of time and effort that you would put into milling the software. So this is the effect. This is the exact toolpath that we need to create, and um, it is slightly easy, but at the same time, it can be sometimes quite tricky when you have a larger list of points. So we'll see how to go about this thing in the next block of code that we'll be looking at, namely this portion. So here I have my set of lists and I've isolated the first and the last using an isolated index. You can always use, there are other commands also, like you can use first, last to isolate the same bit of points. That will also work. So, but I've called out for the first and the last. And then once that has come across, I've moved it up. So I have my original point, and I've moved it up out of the geometry by about 100 units, 100 millimeters in this case. And once that has happened, I've gotten my set of points that I need to move about. Now, once that has done, I have dispatched it. By dispatching, I've created the complete array of first point and the complete array of last points. So these points I've completely gotten out here. So I've added it to the list and merged them together to create a joint list. Now what I have is a list which has the first point. I have the first point, then I have the array of this points, and then I have the exit point out here. So this is my new list now because I've added these two first and last points. Now that is done, I've taken a small shortcut by using this component called divide branches. So what this component does is it isolates one tree. Sorry, 1 second. Yeah, so it isolates every alternate one, and it creates that reversing effect. And I've created it splits the tree into two separate branches, and the second branch I've just reversed it. I've just reversed it to create this kind of to create this divide tree pattern. And then once that is done, I have just put it back into the same list again, because once you divided it and then you reversed it, you need to ensure that you put it back into the same you merge it back into the same list again. And once that is done, and if you were to draw a line, yes, you would create you would see this kind of a pattern where you can see this line going down, and then it is going up. It's exiting from the geometry, reversing it, and then coming back into it. So once you have this pattern ready, yes, your path is ready, and now now all you have to do is send it back into the robot, and it can mill. In the robot, I've tried to use the same logic. I've set up the robot out here. This is my tool. I've set up the TCP points out here. I've set up the axis, making sure that the tooltip is in the right direction, and I've given it a name. I've added the mesh to the tool. I've added it to the robot system out here. Here I've set up the work object. So yesterday, I think we saw how we can get the robot, the work object. The work object consists of the XYZ coordinates and the 4 quaternion components, which is going to be fed. The quaternion plane then feeds into the work object, and this is the work object that you're going to add into the movement component. In the movement component, I'm going to add the planes. I can add the speed to it, the type of movement that I'm looking at, and the work object. I can also add zone data. Maybe I can so in all of this I could add zone data as fine. Or I think I'm supposed to give a numerical value into it. I'm just going to check what is it. Zone data, path zone TCP. Oh, zone data or as a number. So I'm just going to give it a numerical value of zone 0. And yes, that is perfectly fine. And that once that is set, you can just feed them into the components, feed that into and merge them together. So here I've again, as we discussed yesterday, I've first given the absolute J value to home position. I've given it's a joint target that I've fed it into the move component, and the next one is the first move, which is a move J, and then I have the whole set of move L points that is going into the this thing, and finally it is going back to home again. So I've merged all of this, flattened it, and I've sent them back into the path planner and this component. So now I have this created. I'm just going to see how the simulation works. There you go. So it doesn't show, it doesn't give me any errors. But one thing you'll notice is that the TCP is below, the tip is below. You need not worry about this. And if that happens, because what you fed in is the actual TCP, and the actual TCP proceeds over having it how it is visualized in the simulation. Very often in the previous move component, we did not add it, we did not get the actual TCP, but we added the exact tool. So you can either add the exact model with the complete accurate measurements of the space and the tool, or you can feed in the tool center point and the work object location and just give it a movement plan, so that it will still it will look at the actual figures within the actual coordinates of the object and the tool and mill the path. So that this is not a problem, not a point of concern to see this thing, because in many cases the model of the tool might not be accurate. Sometimes we just have a simplistic model just for indicative purposes, and that's perfectly fine as long as the TCP coordinates and the work objects are fed in accurately. These components, the robot will definitely mill according to the data given precisely. Yes, so this is the rough workflow of what you need to do to ensure the milling happens accurately. And once you have that, you have the program G code generated. This you can copy and send it into the robot. Another thing that one thing that we can look at is within this program, there is something called connect get controller. So what this does is if you have an Ethernet cable and you have a port for the robot, you can directly send the robot from out here. So here once you have the robot component, there is a remote connection option which will allow you to upload the code. So once you feed in the robot controller here, and then you would require a Boolean toggle. And again, you'll need a couple of Boolean toggles out here. And it's good to have all these set of toggles connected so that you know the exact steps that you need to take. You need to switch all of them on to ensure that it is connecting and it's uploading and then it's running. Also have a button for stop or a toggle for stop. This is going to be false, the rest are going to be true. You can feed in the program module here and you can feed in the system module here. Right now, since I'm not connected, you need to pass an Ethernet cable from the robot controller to your this thing to get the update. So here again, update you will need. I think here also you need a button. I think you need a button. Okay, let me just check again. Yeah, I think. Right now, one second. I'll just put a toggle over. Yes. But by default, false. Yes. So once it's connected, once it detects, there is a very common error that you will get when you're trying to install this, and there might be an ABB error. One sec, something. Okay, this is ABB robotics error. So if to make sure that this is working, you need to first install ABB runtime environment. And very often that happens that a lot of these plugins, maybe you've installed a robots plus, you've installed robot components, you've maybe installed a version of robodk. All of these plugins who have some connection with who try to connect to ABB Live will offer to install ABB runtime components. If there is a multiple dependency of ABB runtime component, that might create an issue. And if you install ABB runtime component in separate folders of robot components and for robots, that might also create an issue. So try to install it only one time. If you've installed Robot Studio, that is enough. It by default installs robot the ABB runtime component. You will not have to reinstall that again. And once you have that, you can directly send this um, details into the robot. But when you're setting this up, you need to ensure that the robot is in automatic mode, and only then would you be and I think you might have to grant it access. You might have to request access so that you can send information. Once that is done, you will be in a position to send the details directly to the robot. Yeah. So this is the basic rules of how you would go about milling the surface. Um, you can try to do the same thing in robots. The robots plugin, it has the exact same, it has all the same set of components. So, and if you face any issues with this kind of plugin, then this is something that we can let us know, and then we can try to figure out. Robot has the same. Okay. One thing that I forgot, and this is the important thing that I wanted to discuss today, is the signals portion. So here you have here. I'm just going to annotate again. So here I had the home position, and here I have my path coming down, going up all the way here, this way, and all the way till here. This is my last, this is my last point. And from here, this is the direction to go, and here, this is the direction to come back home. So one thing that I need to ensure is that once I'm started to move, I will reach this position first. The speed might be a little faster here, and it might be slower. Might be faster here and start to slow down as per the specification. I what I'd ideally like to do is once it reaches a certain position, I would want to turn my spindle on, or turn my signals on, or turn the tool on. So once this is set, I would want to activate, I want to trigger that event of setting the tool on, and that I can program within this within the Grasshopper component as well. So how do I go about doing it? So say I've reached this point. So this is the first point, and I've started to move out here, and this is the second point that I've reached. Here is where I would want to do a set digital output. And once I have a set digital output, I can click a set digital output out here. Here I'm going to give it the robot controller. The robot controller comes in here. the do name. The do name is what we set in this. Yeah, these are all the do names that that you need to trigger. So if you can trigger it, you can trigger it manually as well if you're setting on the controller, or if you want to program it, you can set the do name out here, and you would probably give it the do name. I'm going to say do1, and then this is going to be the this thing, and you're going to change the state of it. So this is going to be a boolean toggle, and if false is 0, and you're going to set it to a state of signal 1, and yes, update 1 second. Yeah, this will also require a boolean toggle, or like a button. A button will also serve its purpose. Yeah, and you're going to set in the default components. So same thing. Here you will see the toggle. I don't think the toggle is the toggle hasn't inputted out here because we are not gotten anything from the controller as yet. So you set a controller out here, and then you can send it the signal directly. And the other thing that you can do is set the signal and set it to go. And same thing at the end of this thing, end of the final one, you can set the controller to stop. Yeah. Sorry, that was the live one. This is the one that we need to. So you can set this out here. Yes, and this is true. And here I'm going to give this thing. So that I think this one allows you to update it live because it's taking an update from the robot controller, taking the data from the robot controller, and so now this will be we will have it configured out here. Do is there a do1? No. Set analog, wait for analog input. And then set analog input and configuration. Oh, we can set a wait for okay, there's a wait for digital input also. I'm just going to give it a wait time after this. No, I'm going to not set a wait time. Duration is going to be seconds. 500. Let's say 5,000. 5 seconds is going to wait until I'm going to give it like a 5-second time so that it allows you to wait for this thing. Oops. No. Do I robot target? I put it in movement. Yeah. I feed it in the state. Wait for time. No, I don't put it in the target. I put it in. I put it in a code generator. Code types, movement types. I need to go here and I need to wait. I'm just going to put the documentation. Let me just see where exactly I'm going to put the digital signal parameter setup, simulation, code generation. Where do I put in the wait for time? Yes, defines section wait between find the duration based on wait for time control. Usage code generation plugged into the actions input. Okay, I need to plug it into the actions input directly. All right. Let me see this. Here. Oh, okay. Just gonna check what happens. Hmm. Yes, I've added the wait for time out here. So here I've this creates a wait for time. Ideally, I should add it after the J do, because the J do means it's moving moving this thing. So let me just edit this code to ensure that the after the J do, the wait for time happens. So we are going to. So here I've done a replace list because I've changed the within the first list, the first point which was being repeated where I did the J2, I wanted to replace it. So let me just remove I'll just cull the first point and then add this directly out here. So let me do this. I'm going to add this out here. Now I have the wait for time. And then I have here I am going to, instead of replacing this item, I'm just going to cull index. Yeah. So here I put this. I put the index out here. There you go. Then I will list. Oh, sorry, this is the first one. My bad. This is the wrong list I put in. All right, yes. And I'm just going to feed this directly in here. I'm going to delete this. Oh no. Oh yeah. Yeah. There you go. So from home position, I come down here. Then I go to start my movement J, but I start my J do, that is movement J with digital output. I set the digital output 1, and then I uh, wait for 5 seconds as the spindle takes on speed, and then I start to move to the milling thing. And let me see if that is being reflected out here in the code. Yep, after the J do, I wait for five seconds and then I move. Now, I need to do one of the last things that I need to do is after the last point, I need to switch the spindle off. So what I'm going to do is I'm going to copy this component out here. I only want the last item in here, and I'm going to add a -1 out here so that I delete the first and the last item out here. I'm just going to make it into a multi-line text. And here I go. I'm going to give a list item. And I'm going to add -1 because I only want the last point. Here you go. And I'm going to copy this entire set to item. Item out here. And I'm going to put this here in set digital output. But instead of true, I'm going to put it as false. And again, we are going to feed this into the list after this item. And we are also going to wait for some time. Right. But this time we're not going to wait for, okay, we can wait for 5 seconds. There's no harm in waiting. And there you go. And then after that, I directly go back home. Yeah. So I have home. I've come down to the first position, then I do JDo. Oh, all right. This is a small error. All right. I know what it is. The LDO happened out here. Exactly. We know what went wrong out here because it's of the lift. Let's flatten it before the entry because of the different data structure. That got added immediately after the first one. So this is going to flatten all the entries out here. This again flatten and going on. That's also fine. And I'm just going to update the code. There you go. I have JDo. I've got weight, and I start to move around. This is entire. This is all my milling that I'm doing. I go all the way to the end, and there I see after the final, this thing says as an L2, and then there's a wait time of 5 seconds, and then it takes an absolute J back towards home. And this way, the complete milling process set. You can just copy data only, open a notepad, um, save it as a .mod file or a .prg file, and you can open it into the, you can feed it into the flux pendant and open it and run the whole process, or you can connect it to your controller, set this to true, and just feed it up directly. Both will set your robot to run in mode. All right. I think this would clarify much of the process that is required for this thing. Let's take a 5-minute break, and then we will get back to the robots plugin, and we will try to do something with it. Maybe may do a small exercise with robot plugin before we look at other options, including and including how Makina works. So that will keep it towards the end here. All right. All right, we're back. So, okay, let me just clean this code up a little bit. And here you go. So this is a fairly an evolved code we have. We've covered most of the basics, and um, this is evolved code. We've checked out all the problems. Our data structure is fine. Our lists are fine, and our robot is doing the right tasks, including switching on, switching off the components. So and sometime back we saw we saw how we can install robots as a plugin. So I was thinking, as an exercise, we could try to do the same thing within robots thing and see some of the possibilities that a robots components allow, especially the locking of the frames that is allowed. So I'm going to try to do the exact same code out here, but this time in using the robots component. That would be an exercise to try out. So here, let's go to robots. Here you have robots component. Nope, nope, nope. There you go. Yeah. So first things is we're gonna load a robot. Now one second. Before I load a robot, let me just get all the data that I require. Don't need this. The geometry is all fine. I need this. This is what I require. So I'm going to make a copy of this. And I'll bring it out here. Yeah. I need all of this. I also need all of this. Now, robots has a peculiar problem, and that is like, for example, if you look at the mesh, and this has got multiple meshes in it, but the robot tool is far evolved for it to take all the meshes and combine it and just output a single tool. The robots plugin tool does not do the same thing. It requires an input of one mesh only. Otherwise, it will output multiple tools. So we don't need that. So let us see, and I can show you how that functions. Like if I'm here and I'm just gonna just oops. I put it in the mesh, yes. I will get up many different tools, and we don't need this. We need at least one single mesh. So I think I've tried to make a single mesh somewhere out here. Let me see if it is in this file. Move robot. This is the file that requires one mesh. Yeah, I'm just going to copy this. So this is the only one change that we might have to ensure. This plugin is slightly strict. Oh. Oh, there it is. And this is our there we go, we got a mesh. We're going to name it robot 1. No, robot 2, robot tool 1. And I'm going to create the TCP is one, two, three. And I'm going to take this, all of this. And I'm going to feed that into here. Do I require only, do I need to give it a plane, or do I just need to give it a, oh, I need to give it a plane. Yes, that's absolutely. Calibration plane. Mhm. Here you go, and I'm just going to move this aside. Might have to play with this, some option of this, or even change this into YZ, XY, depending on how I'm going to be orienting this. Okay, so now we have our tool set. We need our robot system. Our robot system is here, load robot system. There you go. And we have our robot already set up. Yeah, now what we need is to create our targets. And we also need to create our frame. So for a work object, we're going to create a frame robot system, and we're going to get all right. So in this thing, we're just going to send in a single list of all different numbers. I'm just going to copy 1298.763 minus 413.6208 676.3495 or 0.703733 minus 0.006788 0.00111511, and the last one is minus 71043.
minus 0 point.
Oh, okay. Sorry, I made an error out here. Thanks, Shashank. There I go. Now I need to add the robot system in here. The robot system goes here. Oops, yes, I need to convert this into a multi-line text. Yeah, why is this giving me an error? Oh, text to plain. Plain. Oh, no, I think I made a mistake. Yes, this is what I'm looking at. Sorry. Oh, we had to convert numbers to plain, and now this. Excuse my mistake. Sometimes I can make these errors. Yes. Yeah, so there you go. Now we got our work object ready. Now we don't need this anymore. Shut down. And now this is what we're going to use for our create targets. Now we have we can create two different targets. We right click and we can create a joint target, or we can create a Cartesian target. We're looking for Cartesian target right now, and all the other components that we set out here, we can put it here. We have the configuration input, we have the motion input for our joint motion and other things. We have our tool input, we have our speed input, we have our zone input, and we have our frame input. So here we're going to work with all of this, and I'm going to make this into I'm going to keep one as a joint motion, and then the other one I'm going to keep it as a linear motion. And what else do we need? Command input, motion input. Yes. All right. Yeah. So we have all of our commands coming in from here, and we need to dispatch it as per this thing. So the first one, we broke it down into the first one as joint and the last one as list item. the first point goes in as joint. And here I'm going to give it a speed of say 100. Or maybe let's go faster, like 1000. Okay, let's keep it at 500. We don't want to mill it too fast. Speed is S. I'm going to give it the frame. It'll go in the frame, will come here. Zone, do I need to give it fine or do I need to give it 0? Speed in mm, approximation zone in mm. Yes, robot configuration. Okay. So here I'm going to give a zone. I'm going to give it. Yeah, I'll give it 0. Yeah. There we go. I'm going to repeat this out here. Speed, zone, and here I'm going to feed this out here. And once this is done, I need to send this back out. Flatten the entry. With these two lists, you don't really need to flatten, but nevertheless, doesn't hurt to do it. Okay, so we have, we need to add the tool. We can add the tool out here as well. Add the tool out here as well. But there is another. Okay, once this is done, we need to get the create program. So this I'm going to name it as one. The robot system comes in here. The target comes in here. Oops, so what error am I created? Let us check the errors. Oh, target one of robot near overhead singularity. Let us look at warnings. First target and no, this is fine. This is a warning. Let's change into a joint motion. We need to see how it looks. How is that singularity happening? Let's check out the program simulation. I'm also going to call in the code to check for, okay, the code is not coming in because there is a singularity that is, you see. Oh, this is not good. Okay, I think the singularity arises from maybe this. Let us see. And I'm just going to give it a timeline 0.00 to 1.00. This would give me a time frame to check this out. Let us see how that. Okay, what is this path doing? Let's compare both the robot. Okay, the robot position is like that. So is In the initial positions seem about same except for the frame has gone off. How is the frame? The work object is the same, is it? Robot targets 1, target 2. Hmm. This seems fine. Set size and commands. No data selected. Near overhead singularity. Where is the singularity coming in? Flag fields. No, this is going to be linear. Hmm. Wait, this is tool input. I haven't fed the. One second, 1 second. Command input, external input, join target input. The target input. Yeah, this. I think this is doing what it's supposed to. But there is an error out here. Let me figure out how this is. This is version XYZ. Is there no change in this? This. What tool is 9.x9? How is the mounting on the robot? There's one gap in the mounting, but that shouldn't be too much of a problem. Not at this point. Okay, something is off. TCP. Okay. All right. This is a very weird issue. What is coming out of here? Oh, wait. This shouldn't be. It should be 0. This is the first. This should be. Yeah, no, it should be 0. And okay, even after call index, there is the first point that is existing. Oh, wait, no. No, no. Okay, 100 and then 0. Okay, 100 is gone. Okay, this the point is right. So the entire path by itself is going correctly, but the moment I add the other list, this list, the first point goes incorrectly. Let me add just the second point. Let me flatten this. This is giving an error. The remaining point is giving an error. What is the error right here? First target is trying to this thing. Near overhead, one near overhead singularity. Where is one? Axis number one near overhead singularity. How is that happening? Oh, why is it inverted? Oh, why is it going down? Oh, is my coordinates, work object coordinates off? Yeah, so let me just remove this. Did I not add it here? Oh, I'm stupid. Yes. Yeah. Yeah. So what has happened was I did not add the work object into this thing, and that had created a small issue. Now it should be, yeah. There you go. Now what are the warning? Okay, the errors are gone. Only a warning, couple of warnings. Let's take these warnings seriously. First target, okay, this is fine. One target was set into Selenium with the first configuration. The first one being target one in robot zero configuration, seeing as that's not for automation. All right, so it's adjusted and repaired it. Now, okay, it is going. No, but the only difference is that the work object here and the work object here are at different positions. That we need to know why. Why is this in this position and this work object not taking in these details? Yeah, this is. Oh, do I need to feed in something else? Is it both the same? Is it both not the same? Yes, it is the same. Quaternion to plane. What happens if I feed in this? Will it take it or will it give me an error? Is there no update command? It directly updates. Okay, that's good. Let's check some. Okay, this is peculiar. So even if you're given the same things, the robot does not take in. Okay, it has translated, but it's not taken the z-axis correctly. The z-axis values are not being translated correctly by the robot's component. So this is an issue. So how is this translation going on? The position seems about same. Let us see at this at the end. Yeah, the position is near about same. Yes, only the z values are off. There you go. Only the height at which it is being positioned is wrong. And if I put this out here, hmm. So it's aligned, it's translated to the work object properly, but it's discounting the z-axis position. I wonder why that is happening. Let me see if I can debug. So there you go. So it is in the wrong plane upstairs, upside. Where does Z go there? Hmm. Minus 1, 6, 6, 6. I think it has got something to do with how the global XY is configured, or the coordinate systems are configured, because there is no reason why the code is off. But how the coordinate systems are configured, I think it has got it. But even then, the translation shouldn't be. Although we can never say what is going to happen, what is happening inside the code, because both drawings are from the same position. Both drawings. So here it is. Yeah. So the drawing is at this position. Both are same along the same position, and then it gets translated to the work object out here, and this gets translated to the work object out here. So this is the translation from the drawing space to the work object space. And the translation is happening in the right position, except with the exception of the z-axis. This is something that I don't know why this is happening, but yes, I would like to figure it out. But yeah, I think the code is working. This plugin can also work. I think we have a trail function that you can add out here, simple trail, to understand what else do I need to ensure that the index of the mechanical group 0. Okay, now number of trail, I'm going to give it 5. Oh, 1 second. Why is the trail not working? Oh, 1 second. Do I need to output this as a line? Oh, sorry. The value is inherited from source. Why? Okay, something is happening now. Okay, maybe this is not the plugin that I thought it was trying to be. Maybe robot components is definitely a better plugin that we can look up to in terms of all the function that it offers. But yes, but yeah, this is something that we can look at. Create speed, create to create check for positions, custom G code, merge KRL, kinematics. So I'll take a look at why this translation is not happening in this thing. But meanwhile, we can always try to see where the position is. Maybe even build the work object out here and then try to position it on top of it so that there is no errors happening because of misplaced translation of the work object coordinates. Yes, but and the other news, robot components works pretty well for the same set of things. We can always add command input. Yeah, okay. In the command input, you can always add the set to command. There you go. So all commands can be added out here. Do1, do. Wait, what does it require? Data field to convert from text to integer. Okay, maybe it doesn't require this thing. Yeah, just give it the value and it will take it. Do1 value is 1. Let us see how it adds. Set do, yes. Sync do1, move absolute j, sync do1. All right. I'm just going to add another wait command. Do we have a wait command out here? Yes. Wait. Give it 5,000. Wait for 5 seconds. Let's just merge all the commands. And feed it into the command situation. How does it update? Okay, set do, then there's a move j, and then there is a wait. That is wait. Wait, move, which move ABS is this? ABJ. Trying to move J. Move absolute to this join position. And we did not set a move join position, but there is already one. Here I'm going to copy all of this. So -1. Multi-line text it. Last one, and this is again 5 seconds. I'm just going to make it value 0. So and this is the last the bottom step. We're gonna switch it off. Oh wait, I need to add this into this. Flatten. There you go. Set to move J. Wait time. All right. Maybe I think we need to do a set do. We need to switch the move J and then the set do. Yes, this won't work. So we'll have to do another set 2 after. Uh, let's try to do the final configurations. Maybe after this motion, we'll do a set 2 because right now it is doing a set 2. Does it go at the same time? Fine, speed, robot tool 1, frame 2, sync set 2. Whereas we see the set 2. This we'll have to check it out actually, but because this is doing a direct L do, I know for a fact that it's gonna move. Oh, it's gonna stop and move and stop. And then wait. Okay, maybe it will sync. It will sync both of them together. All right. And then lastly, we need to set define joints. 30. This is going to be the home position. And I'm going to do a create joint out here. Sorry, create target. And right click, change it as a joint target. This is going to go back to home. Yeah. There. Oh wait, this 90. Why is this 90? 489. Second axis is 90. Yeah. Yes, 000. Okay, this is something weird. This is slightly weird. And I think it has something to do with how I've configured the robot. Because 0 is coming here. So maybe this is an error in how I modeled the robot. Because my 0 has changed. But when I put it on 90, because when I'm putting that in code, it is showing it as all other things. So yeah, there is some issue here that I need to figure out. But yes, this is the home position. The robot is back in place. Wait, where is the tool? Oh, the tool is not there. One second, I'll add the tool so that we can see the tool. Tool input. And I'm going to add a frame input, command input, speed input. I didn't have it. Okay, this is going to go back into starting as well. We're going to start from. Yeah, you go. Okay, this I really need to check the model minus. Okay, this is minus 30. This should be plus 30. All right. This is how the tool is looking in the normal position. Zero 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 30. Well, what is happening out here in this code? 0 0 0 0 0 0 0. Didn't I change this to 30? Oh wait. 30. Update. Yes. Let me say this and Okay, this is in the exact opposite direction. I think the fifth axis is also off slightly. This probably needs to be 180, but it's showing 0 here. What is minus 30 then? Minus 30. 180. Wait, this is axis 6. Why is it going there? Oh, okay. 0. All right, I think my fourth axis was flipped. I need to check this model again, whether this is the reason for why things are going off. 0, 90, 0, 180, 30, 0. Yeah. So this is the entire code for the ABB robot. And there you go. Everything is set. And we can simulate it out here. Near about the same thing, except with the z-axis error. Two things we need to check it out. One is why the z-axis is not translating into the work object, and why the whether if there's a modeling error or is there a frame reference error in the model that I figured. Let me see if there is another ABB model that I can check out. ABB. 4606700. This is a big model. We can check the Nagami IRB 6700. And how does that work? Oh, maybe it is not our modeling error, because this is showing perfect with this configuration as well. Let me see if it is a robot specific issue. Let's try a KUKA. Yeah. How does wait, this is a very different KUKA. Let me check a KUKA TX21. This is a big KUKA, right? This also folds in this home position. Yes, this goes for a toss. There is errors out here. But this is maybe too big a robot which is facing singularity issues, but let's take a KR. Why is this an issue? Maybe the robot system will not take. Maybe is this plane only for merge KR? Let's import KR. What is the error? This should be made out of 6 numbers. 1, 2, 3, 4, 5, 6. Okay, KUKA takes in only 6 numbers, whereas ABB takes in 7 numbers. Let's say I'm going to delete this number. Control X. All right. And what is the error KUKA will give? Have wrong number of external. So this is the robot with an external access. Let us change this to something else. AKR60. Okay, again, something with an external axis. Everybody's got external axes. This is a UR robot, definitely out of reach. Yep, not the right robot to test our errors. AR15. I think our robot configuration is the right one. This is also giving an error, but it is, at least it is fitting in the same place. Cannot do any of this. But at least the 0, 0 position is the right one. So I'll just check the documentation about what it has to say about why is the joints defined this way, and if there is any way we can try to rectify this. But it seems that this is the right configuration of for the normal levels. Let's open the documentation and see if there is anything to do with joint position. Joint target. One second, let's see target. Target defines robot pose, how to reach event, gets a tool path made out of from list of targets beside the function of the tool. The pose of the robot defines the rotation values and let's define the pose should be a joint target. Let us look at pose robot libraries. Is there pose out here? Motion type configuration. Installing, editing a library, publishing it. Clone this okay. Install along warnings, program remote connection, castings, frame zone castings. String of numbers, plane with a Cartesian target will create default variables. Okay, the pose defined by the preferred Cartesian. Targets can produce singularity, the most common being express singularity. This happens in the desired position and the orientation requires. All right, so this is the error. This is the kind of error that we see in that I was speaking about, the fifth axis being in line. And the fourth and the sixth, they are in single plane. This is the same axis. I think I mentioned 5/5 axis. That also changing that also creates this thing. But one last thing that I wanted to show in Robot Studio is the wrist configuration. We are going back to our code and going to select our robot again. Oh, all right, 1 second. Yeah. Now let us play with something like the wrist configuration. Whereas I'm going to check in the elbow and then see what movement it creates. Yeah, so it fixes the elbow. All right, maybe this is not the right example to show that, show the wrist configuration, but what essentially we can try to do is fix one of the joints so that it doesn't rotate around to create some sort of singularity. This is especially helpful if you're trying to rotate the entire, if the curve rotates at a in maybe a higher degree, and then the frame, the tool tries to follow the frame and tries to wrap around into itself, try to create a singularity. What this will do is it will try to fix the tool path, fix the joint elbow without allowing it to go in the other direction. So this is something that we can experiment when you're trying to solve this. But I think we can hold this at this. We can hold it at this position, and we'll take a small break, and we'll come back and we'll check out. We'll look at Machina and the kind of possibilities that offers, especially. And I will see if we can try to configure the robot onto to test the Machina program. All right. I am going. We'll be back in 5 minutes. Okay. All right, we're back. So there has been a slight issue. We were to look at this really interesting program developed by Jose Luis Garcia called Machina. What it allows is it allows for us to um, communicate in real time with the with the robots and things across cloud. And we were really trying to do a demo, but apparently due to some technical difficulties, we will not be able to do it. Particularly, it's got to do with we can't run a parallel stream along with trying to connect the robot, and to do with the fact that it requires a certain bit of configuration that might take some time to get this thing. So uh, so that hopefully what I can try to do is maybe record a small video on how this is happening, and maybe upload the file and this thing into the same drive, and you can have a look at this thing. uh, you can have a look at the file that you can have a look at how Machina works. And that is an interesting aspect or something that we can look, especially when we're looking at cloud computing and real-time computing. uh, this is something that we will be interested in seeing how it works. But I think we've covered most of this thing, including printing. One thing that we haven't looked at is pick and place. But I thought if anyone is interested, they can give it a go. Maybe try to develop their logic to how a pick and place uh, how pick and place might work in this thing. What I can suggest is small hints on this uh, how this can work. Particularly, you will have the set of you'll have a block located in one position. I'm just going to annotate in the screen. Um, one second. Yeah, so yeah, if you have a robot, this is the robot. Then you have the with the gripper on board. What you will try to do is this if this is the work object, there will be one location maybe outside the work object where an object that you want to pick is located. So this is the point where the robot is going to reach each time, and then it's going to stack up in different position that is available, maybe here, maybe on this a couple of times, 3 times out here, then move on to this thing, this position out here, uh, and place it out here. Or maybe you can try to create a wall. So few things that must be kept in mind is to start from this thing. You need to identify this position, the center and the top of the brick onto which the robot is positioned. Move it up, clear it to a point X in space. From there, it goes vertically to a point Y, where it's going to be, which is going to be above the location where it's going to rest. And finally, it is going to be positioned on the work object plane. And this thing is going to be repeated 3 times, maybe 1, 2, 3, or how many ever times you want to stack that object. And once that is done, you're going to move on to the next position out here, stack it up here. So each time there is this is a constant. Even these 2 points are constant, but these points constantly change, and they will be sent in as a list, one after the other. This thing, maybe you will have this point, maybe let's call it x1. One second, I'm just going to control C. Sorry, I'm going to call it x0. This is x0 and x1. Once it reaches x0, it will you will do a set do to okay, I'm just going to do, just going to plus, is going to activate the gripper, then it is going to go to x1. Then from there, it is going to go to y1, and finally y0, where it is going to be do minus. We're going to switch that off. Then from there, it is again going to go back to y1, x1, and x0. And once it is reaching out here, it's going to set to again, where you're going to start the gripper again and then repeat the whole cycle. But the only thing that is going to change is y1 in the next list and this thing. So you might have to have one list which has one small list which has x value, or one list which has x1 value, and then 0, one grasshopper list of y1 and one grasshopper list of y2, y0, and then try to weave them all together. Weave them in grasshopper so that you can get an space list. Similar to how we weaved it in the milling thing, where we try to add 2 at the ends and then try to reverse split and reverse. Maybe try to work out the data, the list logic, the list manipulation. It's tricky. It's slightly tricky, but not impossible. Reading the list is far more important, but it is something that you can attempt to try. So once that is done, maybe we can try to see how you come up with this thing. But one of the things is that we've been looking at is how you can work with, if you have any projects that you're attempting, or if you are interested in trying to check out how one of those robotic fabrication systems might be helpful in your workflow, then that is something that we can explore or experiment with, and we can see how best we can resolve this, or we can find solution for your problem, or your robotic fabrication problem. So that this kind of concludes what we were planning for today. Two things could not. One thing that we really wanted to look at, that was Machina, could not happen. But we will. We will set that up for some time during this week. We'll share the files, maybe with a small clip of how that is being implemented, because trying to stream from the robot while I'm trying to connect the network, that creates a small issue. And yeah, I will not be able to stream, and the best thing I can do is the shaky cam, which might not be the best way to document how the thing works. But it shouldn't be a miss. I will share with you the Jose Luis's setup. He has 1 second, I'm just going to clear my screen. Yeah. What was this? Yes. And there is a whole set of videos also. Machina, is it in parametric again? Let me see. I think it is there. It will be there in the. Yes, this is the paper in which he's described Machina and this thing. 1 sec, Machina GitHub. Oh, okay, what I'm searching it in the wrong this thing is. Yeah. This is Jose Luis Machina. Oh, yes, here he has Machina.net real-time robot control for this thing. So you can check this out. This uses built on the .NET library. It's a fantastic app that he's developed, and it has, and I think of lately he's developed a real-time implementation for KUKA as well. So that is another great thing. Otherwise, it was up till now, it was a real-time configuration for the UR robot and ABB. So do check this out. He has a set of Grasshopper plugins as well, a Grasshopper plugin also. The only difference is that it has a slightly different logic to it. Um, uh, 1 second. Yeah. Yes, so it has a slightly different logic to it, where how we set up the speed and the angles and everything is slightly different. It is not like robot components and robots have the same logic to it. This might be slightly tricky about the angles being in degrees and the um, rotations and everything's to be a little different. But once you get a hang of it, it is something that you can do. And once you've set that thing, you can directly send the code to the Machina bridge, which can stream it directly to the robot. So here you can see all the set of commands. The commands are sent differently. Here, I think in the bridge translates it into a rapid code. So all these commands, namely the message, the initial speed, or the points, and all of this, the actions, they are sent differently, separately. And the ones that are sent, this is the set of commands that is sent to the bridge. And once the bridge, that is collected, and then it is sent to the robot. What it uses in the background is a WebSocket, and the WebSocket. This is the code generator. You send it to the robot, and it generates the code. And yeah, there you go. This is the code. So what it uses in the background is a WebSocket, which you can use to communicate with this thing. The other app, or the other plugin that I was speaking about, Bengest, that is also used to send data across the internet using WebSockets. So that is also something that, given the time, we will not be exploring. But if you want to send remote data, then all you have to do is create a small WebSocket, use Bengage to start a to create a client-side server. And one thing I can show Bengage a little bit of right now. So it is pretty. We will not be creating a WebSocket, but I can show you the logic of how that works. So you have these three components: the WebSocket, receiver, and this thing. So when you start a WebSocket, what happens is you need to first, here, this is missing, yes. Here you will set in the WebSocket address and maybe an initial this thing. So it will be ws dot IP number, something in the ws dot whatever IP number of the where the client is residing. That is what you're going to send it here. You're going to send in an initial message and a reset, and you are going to send that. If you want to send it, you're going to connect the WebSocket out here, and this is going to send it. If you had to receive WebSocket, and if you are a client, or if you want to send it from the receive it from the other side, then this is sorry, this is the sender and this is the receiver. Yes, I'm sorry, I interchanged it from there. So you can have these things. This is all it takes, and then you need to build the WebSocket on the backend, and you can access it directly. This you can interface it with your robot components. You can, once you send in the data, you will probably send the program module data, more textual data that you can send it across, and that can be received and directly sent to the robot by a client side who's sitting on one side, in the other side with the robot. So that is one way we can look at trying to communicate real time with Bengist and other robot component tools. So yes, so these are some of the things that we wanted to discuss today. And if there are any questions, then we would like to take them. And And if you have any other queries, or if there are any projects that you would like to develop the robotic fabrication toolpath for, that is something that we can look at right now. Okay.
Is everybody clear?
Hello. Yeah, okay. I think if there are no more questions and this thing has been clear, we can end our video right now. And if any other question or any other problem arise, you can reach us at our emails and we can get to know. Meanwhile, we will update the uh, repository, the Google Drive with the two files, one with the Machina in it. And if anybody can attempt the pick and place program, then that would be something that we can discuss. So any outputs that you have developed during the course of this workshop, or you will be developing, do send it to us. We would be interested in creating a small, we have to create a small presentation for the digital futures, this thing about the kind of outputs that have come out of it. And we would like to document your work and send it across as something that has been generated by the participants. So this is something that we would like to get from you, if there is some outputs that you can comment. But which robot arm do you suggest to start with? Good ratio of price quality. For learning, I would definitely recommend a UR robot. It is a small, versatile robot that can fit in the classroom, can sit in the sit within the workshop. It has a lot of newer sensors, such as force feedback, and if it was to you can have it you can have the force sensor to stop. Yes, you have the UR3, UR5, I think there's a UR7 and the UR10, all of which can be mounted. I think the 5, and okay, that's 5 is something that you can look for to fit in this, and it's something that you can learn. The interface is pretty easy and it is programmable. All our plugins also you can read the plugins also. We have a numerous plugins for this also. Even Machina can send real-time information to the UR robot, and that creates a lot of it reduces the risk of experimenting. You can attempt a lot more things, and it is quite friendly in you, and yeah, it will not hurt you. There is no risk. The risk to you is far less with the UR robot with its force feedback, where if it was to hit an obstacle, it will stop rather than push through, as compared to some of the other robots that you have. So, and very easy UI, easily programmable. The UR language is not as complicated as Rapid or even KRL. So that is something to look forward to. In terms of price range, and if you compare it with equivalent small robot, it might be slightly on the higher side, given the number of sensors and all that it comes with. But I think it's a good start. Apart from that, I think what other small robots are there that you can start? The ABB 120 and 140 are good robot, but then again, the price range is slightly on the higher side. I think KUKA has some newer robots, but yeah, but my bet would be on the UR. in terms of learning, in terms of interface, in terms of all the other things. I think other smaller robots, I think Epson and Fanuc are also developing some smaller robots. But yes, that is something that you can attempt to start with if you want. Yeah, sure.
Okay, then I guess we end the workshop today, right now.
Yeah.
And as Sujay suggested, that whatever you guys are working on, if you need any questions or doubts, if you have, we'll be more than happy to at least write back to you. And we'll update our repositories, and we'll also send you the video recordings. And it was a pleasure having you guys on board. And I hope you guys did get something out of the last 3 days.
Yeah.
And we look forward that you use these ideas, whatever we have shown. And
And I think DigitalFutures will send across certificates of participation or something like that. I think we just got a mail today, and once they send it, we'll forward them across to you. Once we receive those, I think they send it directly. Last time they sent it through through us. Maybe this time they will send it directly. I don't know exactly. Their interface is slightly buggy, so good luck. Well, thank you very much for all of this. And if there are any other queries, feel free to reach us via mail or via Discord. Yes, there were some plans to do a lot more, but we realized a little bit that some of the concepts are a little challenging, especially to do online, and especially to try to connect the robot to the net and try to stream online. We were facing a couple of technical difficulties. It's not that we didn't want to do, but yes, over that. I do plan to make a set of video series about how to configure all of this thing, and maybe once that is ready, we'll share it on Discord, and we can have a discussion about it later on. But yes, this was interesting. Yes, and we would always love to know about any other projects that you all are working on, with whether it regards to architecture or anything to do with related to architecture or digital fabrication. We are more than we are quite inquisitive about the kind of works happening. It is quite engaging to have these design discussions sometimes. So and it's sort of like a learning process for us as well. We're constantly trying to learn about new things. The technology and the design education is evolving quite a bit every day, and we would love to hear more about your work. Yeah. All right. Thank you so much for sticking around. This was quite a fun session that we had. Hopefully in the future we'll have longer sessions. And if ever you get a chance to visit India, and especially in Mumbai, to come across, I would love to host you all in our lab, and we can play with some of the tools that are available to us at this point. Yeah. Okay. Thank you so much. Have a good evening.
Thank you so much, everybody.
Thank you.
Have a good evening. Bye-bye.
Bye. See ya.